Okay, well, thanks for inviting us.
Yeah,
So
I'm going to get started.
intro first.
Gonna introduce you first, and so welcome everyone to this week's NL seminar. And today we are very delighted to have not only one speaker but two speakers, Sören Mindermann and Jan Brauner, as our special holiday retreat and the last talk for this year. So Sören is a final year PhD student in machine learning at the University of Oxford, supervised by Yarin Gal. His interests in machine learning include how it scales, causal inference, and statistical modeling, as well as robustly aligning machine learning models to adopt human wishes and value. While Jan is a PhD student in the Center for Doctoral Training on Intelligent and Autonomous Machines and Systems, supervised by the same Professor Yarin Gal. His current research interests include AI safety and applications of AI in medicine and biomedical research. Today, they will both give a presentation on prioritized training on points that are learnable, worth learning, and not yet learned. As you already know, there will be a QA session at the end of the talk if we still have room for it. Otherwise, you feel free to ask your questions at any time during the talk. And as usual, please continue to mute your mics unless if you have a question to ensure the clarity of the talk. Thank you again so much, Sören and Jan, for joining us today, despite the time difference with Europe. And I hope you enjoyed the talk. And please note that the talk will be recorded but not posted to YouTube right away. Yeah, I will hand it over to Sören and Jan. And thank you.
Okay, thank you as well for inviting us. Yeah, so this paper we're talking about is called Prioritized Training on Points that are Learnable, Worth Learning, and Not Yet Learned. And aside from me, Sören, and Jan, who are talking today, we have a bunch of co-authors from Oxford and also from Cohere, which is a language modeling startup you might have heard of. Right, so let's get started. So let's start with the motivation, which is that we all know model training can be very slow. So for example, language models some of them are trained for months, and that's just for a single training run for the biggest ones. And it's getting really hard to bring that training time down in the sort of conventional ways that people use, namely parallelization. People have been increasing batch sizes more and more, training on lots of data in parallel, but this has diminishing returns. Which is because, which means that, big labs at least set their batch size to the maximum that is still efficient. And so increasing it further becomes like no longer very useful. But this is intuitively, this is because once your mini batch gets really big, the mini batch gradient gets close to the full batch gradient on the whole data set. And so if you're already really close to that optimal, to that sort of ground truth, well, there's not much closer you can get. And then there are other ways of parallelizing to reduce training time: width-wise parallelism, depth-wise parallelism. They also have similar diminishing returns issues. So given we're running into diminishing returns there, how else can we use extra machines to reduce training time? This is our starting point. And yeah, as a quick note, we use in this presentation, we're going to be using as the measure of training time, we're going to be using the number of training steps. So we aim at reducing training time, but not reducing training compute. And training time is often measured by the number of training steps. But our method does have overhead, some costs in terms of compute that are not accounted for by that measure. But we use this measure because it is it's sort of the most defensible scientific measure of training time. But keep in mind there are costs in terms of training flops. Okay, Cool. So let's get into it. So model training can be very slow, but lots of the computation and time is wasted on points that are redundant, noisy, or less relevant. So to give you some examples from MNIST, on the left one here is a noisy sample. The sample has been mislabeled as 6. It's been mislabeled as a 9. We don't want to prioritize those points. Then in the middle, we have a sort of nonsensical character, which we also don't want to prioritize training on that because, well, we're less likely to find points like that at training time. These are basically like points with low input density, P of X. So for the purpose of reducing our training loss, they are less important, although not unimportant, not totally unimportant. And then on the right, perhaps most importantly, there are in all across machine learning, you will find redundant points. You'll find points that are easy, which, you know, the model is quickly able to do them. And then we spend lots of time training on those kinds of points, even though the model has already learned them and has a low loss. So we want to skip all of these types of points if we want to reduce training time. Now, one sec. Yes. Now I used MNIST here, which is the most popular vision dataset. Not the most popular maybe, but it's a classic one. But these types of examples are even more common in web scrape data. So you'll find across language modeling, vision, that there are lots of points which are just sort of redundant and too easy. Lots of points, you know, that are noisy, where the label is unpredictable or is just simply garbage. And yes, and there are lots of differences in how relevant different data points are. Some examples here from ImageNet. So before we get into the method, this is like a quick teaser of figure 1, the headline result. You know, other sort of existing data selection methods typically get speed ups of around, you know, reducing training sets by 50%, by 2x, 3x, in some cases 4x. But where this method is really going to shine is relatively big, noisy data. That is, and there we get speed ups of up to 18x, which is sort of unheard of in this literature. And yeah, we'll see more later. Okay, cool. So how do we actually do this? Okay, so as a background, there is a framework which we call online batch selection. So we start with our big data set D. And as you do every day, we draw large batches from it using uniform sampling or uniform shuffling. And but in our case, we don't just train on that large batch. Rather, we pick a sub batch, a small batch, lowercase b, which should consist of the most informative points. And we can skip the rest. And the way we do that is we have a selection function which scores points according to, well, some measure of how useful they might be. And our contribution, and then we train on that. We train on that smaller batch, saving the compute on the points we left out, and then we just repeat that in a normal training loop. So it's quite a small change to a training loop. But the thing that we're contributing is that selection function. Which points should we select? And our answer to that is going to be the reducible holdout loss, or RHO-LOSS, which is a pretty simple but principled selection function, which selects the points that, approximately at least, the points that should most reduce the model's generalization loss. I think I can hand over to Jan here. Are you on mute?
Muted.
Yeah, I think you unmuted.
Sorry, and now I'm unmuted. Can people see my screen? Sören,
Yeah. This is a different objective.
Okay, great. All right, thank you. So we're doing online batch selection, and then we need a function to determine which points of our large batch that we sampled is going to be included in our small batch that we actually use for the gradient update. So standard online batch selection method that like many people know is loss selection. So you just take the points that have like the highest loss. And so what this selection function aims to do is to select those points that if we were to train them, minimize the training set loss. So just stepping through the notation here. So we select a point xy from the large batch capital B. And we select this point such that here the train set loss is minimized. So this is a prediction task. So you can also frame it for other tasks, but here's prediction. So we have the train set loss minimized of a model which has been trained on all the data we've seen so far and on this point which we are selecting. So basically, if you were to not approximate this objective, you would have to take your model, train it on every point in your big batch, and then figure out which of those points actually minimizes the training loss of the model. So that's obviously too expensive, and so nobody does that. But instead, we do things like loss selection, where we just selecting those points that currently have the highest training loss, with the rationality of, well, yeah, if we then update on those, the overall training loss will go down. Gradient norm selection is also, I mean, gradient norm selection is then approximated, and gradient norm selection itself is also an approximation of basically, of the same objective. So our objective is it's a different one. So this is our objective, the RHO loss objective. So here we're looking for points that if you were to train on them would minimize the holdout set loss. So this looks the same as above, just that we have like, we no longer look at like training loss here, but like the holdout set loss. Well, this obviously has the same problem that it's not tractable. So basically we're trying to find the point that would most reduce the holdout loss if we were to train on our current model on this point. But that's like, if we actually just do this, we just train our current model on every point on our batch, it's super expensive. Train and then evaluate. And so we need a different way of doing this. So now I'm going to show how we're doing this and how we're kind of approximating this, gold standard objective. So there are 3 approximations. All approximations are mostly justified empirically, but I'm also going to give some intuitions for why one might think that these approximations are justified. So here is kind of like the first part of the derivation. For readability, I switched the sign, so I just dropped the minus here. And yeah, I mean, this is just algebra. And here in the last line, we just dropped kind of like the conditioning variables we didn't need, and rearranged a bit. And yeah, you use the definition of the negative log likelihood losses. And yeah, so that's what we have. So So in order to be able to do all of these steps, we're assuming like a probabilistic model here, right? Just using laws of probability. Yeah, we obviously cannot do this exact conditioning in neural networks, because exact inference is intractable in neural networks. So that's the first approximation, is that we are not actually conditioning our models on all of this data, but we're doing the gradient updates. Yes, ultimately this is justified empirically. We have just some experiments about this in the paper, basically. So now what are these terms? So the first term basically is now the loss of the point xy. So this is kind of like the same as loss selection, this first term here. The loss of the point xy under the current model. And the second term is again the loss of the point xy, but here we have a model that is also trained on a holdout data set. Yeah, so this whole second part is new. That wouldn't be part of loss selection. So this is cheaper now than testing every point in your batch and updating your model on every point in the batch and then evaluating the model. But it's still pretty expensive. For example, you have two terms here, and they both need to be updated whenever you acquire a new point because the dt changes. So another simplification we can do is that we take the second term here and we just drop dt from the conditioning set. Yeah, so if you do this, first of all, why would this be good? Well, it saves like a lot of compute because now we can just take the second term here and we can just calculate it for every point once at the start of training. We don't have to do it again in each epoch or something like that, because there's nothing that changes over time here because there's no more t in the conditioning. So that would be good. So empirically, this doesn't hurt our performance at all. It actually has some helpful properties when you combine it with the first approximation, which is that you don't use full Bayesian inference, but approximate it with stochastic gradient descent. Yeah, now we have these terms here. So we call this term here, we call this the irreducible loss, because this is the loss that you get on the point xy under a model which was trained on the holdout set. And so basically, if this holdout set is large, kind of the limit of that being large, you would say something like, oh, this is kind of the best loss you can get on the point xy if you haven't trained on the point xy itself, right? So if you're out of sample, it's the best loss you can get. So we call it this irreducible loss because you can kind of only reduce it by overfitting or something like that. And so then the first part, well, we call this the reducible, no, sorry, and then this is just like training loss. And so the whole thing, the whole difference, you're calling the reducible loss because it's like the training loss minus the reducible loss. So this is the approximation 2. And now the third approximation is that
maybe because this is like the most technical part, if anybody has like some clarifications or questions to ask at this point, let us know.
Let me just run through my understanding of this. So loss of y given x parameterized in d sub t, that means you have a model that's been trained on d sub t is all the training data?
Yes, no, it's all the acquired data.
All the data the model has been trained on so far.
So far, right, okay. So, and then, and it's just, so far, it's like wherever we are. And then the y, and then the second term is you just train a model on some held out set, and you're going to train that right at the beginning. You choose some held out set, and that's going to be completely invariant. And what you're actually calculating is the loss of this thing. So there's no like the thing where you like try to add just xy, right? You're just saying what is the score, what is the error?
Yes, exactly.
What is the difference? And so you're going to just, so you have that fixed for, you could do that fixed for all y given x in the training set at the beginning of time. And that's what your second term is. And then your first one, you would have to do it for the current step for the mini batch, right? And you're picking, so it's the thing that, you're picking the thing that maximizes this, the y given x that gets the biggest difference.
Yes. So there's going to be slides later on why this kind of, yes. Like in loss selection, you're also picking the point that has currently the highest training loss. And so we're also picking these points, but we just do something else with them as well.
Okay, the idea,
I'm not sure if this is in later slides, but we're actually going to pick a set of points rather than just one point. Okay.
Sure. And presumably you'll tell us about how you find an interesting DHO, maybe not. Maybe it's just a random holdout set.
Sorry, what was that?
The DHO, are you going to discuss the interesting?
Oh, the holdout set. Yeah, it's just random.
Oh, it's random. Okay. So the idea is like kind of like if the thing is still, it's a really big difference from the from what's it seen versus some held out set, that's indicative. Whereas if it was just a large value, that might not be indicative. The intuition there, kind of. I'm trying to figure out the intuition for that second term.
Yeah. So maybe, okay, I'm just going to do intuition now, right? So the point is that, for example, so let's say you have a point which is mislabeled. So mislabeled by where the gold standard is like, I don't know, some a panel of like human experts or something like this. And you say this is the gold standard. And now you have a data point which is like obviously mislabeled with respect to that gold standard. Then so we know that mislabeled data points have higher loss over the course of training. Basically, model takes longer to kind of learn these points, and so with what if you use loss selection, you'll just fairly often choose to acquire and train on these mislabeled data points because they have high losses, right? But now. Okay, but there are also just data points that are not mislabeled that you just haven't learned yet, and they also have high losses. And these second ones, you do want to acquire them. And so you have this problem where if you only use the first term, you can't distinguish between, well, points that are like you haven't learned yet, but that you would like to kind of do gradient updates on, or points that are just mislabeled. And that's why you're mispredicting them. And so because they both have a high training loss, but the point is that, like, at least on average, the correctly labeled points, they'll have a low irreducible loss because, well, if you have a model which is trained on holdout set, then it will be able to predict these points relatively well. But like the mislabeled points that also have like a very high loss here and a very high loss under this model. And so the difference then comes apart, and this is kind of a way to, for example, distinguish like points you haven't learned yet from mislabeled points. And there are more intuitions like this.
Right.
Yes, they come later.
So does that advantage then disappear as d sub t gets bigger than d sub ho? Because once the model is well trained, the main model is well trained, that behavior should be true about dt. But initially, that intuition definitely holds, right?
So,
yeah. So the funny thing is, so this gets into basically what if your training model, which we call the target model, the one on the left, gets better than the one on the right, which we call the irreducible loss model. And it's kind of surprising, but it still works, and we're going to see later why. But in the upshot is we're still selecting points that are learnable, worth learning, and not yet learned, and that doesn't really depend that much on how good this irreducible loss model is.
Okay.
yeah, I think an intuition is that even if like dt gets large, okay, never mind. I was going to say something about overfitting, but it doesn't really fit into the theory because the theory doesn't really assume multiple epochs. So yeah, I think that's what happens in reality, is that like you can still overfit on points, and then that plays a role. I'm going to move on here now. So last way to make this objective more tractable is that we are now just so far, I mean, yeah, implicitly these are all kind of the same distributions we're kind of moving around. So same models, same architectures, but it turns out you can just replace this irreducible loss model with a really small model, which is pretty cheap, and you can use a pretty small holdout set if you want, and so on, and the whole thing still works. So yeah, we definitely have in the paper models with like way fewer parameters that train for fewer steps, that have like way fewer accuracy than the target models, and still speed up training by 10x or something like this. Why that is because, well, you still have all the properties that, well, we show empirically, you still have all the properties that we care about. We are still skipping points that are already learned. We are still skipping points that aren't learnable because they're mislabeled, for example, and we're still skipping points that are not worth learning. I mean, in some sense, this makes sense, right? So, for example, let's say we want to like skip not learnable points. So the property of whether a point is learnable is kind of within the set of models that we are like considering, is kind of a property solely of the data point and not a property of like the combination data point to model. You know, because it's just if it's like an image of a cat and it's like labeled as dog, then it's just like mislabeled. And at least within the models that we're considering, which are all kind of like models that only have the image itself as input data, for example, then it's just more like a property of the data point, really, and not so much a property of. It doesn't really depend on the model. So it would make sense that you could use a just smaller, less capable model to filter out these, let's say, mislabeled points. Yeah, and also often you just, you know, if you make your model a lot cheaper, like 30 times, 50 times, 100 times cheaper, and then your accuracy difference is maybe like 10 percentage points. So it still means that like on up to 90% of points, the models have like the same predictions. So these are like some intuitions for why this would work. Yeah, if we have this now, so we kind of say, oh, we can use a fixed small irreducible loss model for this algorithm. Then we can also use one model, amortize it across, for example, a hyperparameter sweep or like a architecture search, which is just what we actually have. We have experiments on this. So let me quickly, yeah, exactly. So now I think now is like the part where that conveys like most of the intuition. I think maybe I want to have this earlier in future talks. Okay, so we have this reducible holdout loss, which is a principled approach for approximately choosing points that would most improve the generalization loss if we were to train on those points. But we are not actually training on the points because it's too expensive. And here is how it goes. So we are, apologies, this is now argmax now, because I shifted the sign, it's easier to read. So we are picking a point xy out of our large batch that has a high training loss. It means like the current model cannot predict this point well. The current model has high loss on this point. So that's loss selection so far. And if we do this, then we're definitely selecting points that, well, the current model hasn't learned yet for whatever reason, right? But the thing is, if you select these points, they could have a high loss because, for example, they're just unlearnable, noisy, or because they're not worth learning. At least if your aim is like good average predictions, then you just don't have to learn all the wild outliers. So how do we improve this? Well, we subtract the second point here, which is the irreducible holdout loss, because noisy points or points that are outliers that are actually hard to predict if you just have a holdout model, and that means they have a high irreducible loss. So in summary, the reducible holdout loss is low for points that are already learned because the training loss is low. It's also low for points that are noisy because the irreducible loss here is high. You're subtracting a high thing. And it's low for outliers, points that are not so relevant for prediction. Again, because this thing here, second term is high. But it's high for points that don't have any of the properties. It's high for points that are learnable, worth learning, and not yet learned. Yeah, that's the intuition. Yeah, I think I'm going to wait until somebody says they have a question, but questions are always welcome if there are any. Next thing, I would step through the algorithm real quick and then be sure. Besides, yes.
So just to recap and make sure to understand correctly. So in this equation, the second loss term, the irreducible holdout loss, that is assumed that is calculated by a held out fixed model that can be really small, right?
Yes.
I see. Okay. And so the only model that gets improved is the model that's responsible for the first term.
Yes.
And in that sense, would you like, and not incompletely, but would you like use the similar terms that they use in distillation, like student and teacher? So the model responsible for the irreducible holdout loss, it's sort of a teacher for selecting the points for the bigger model in this case. I know. Yeah,
this is sorry.
I know that this is not a strict distillation situation at all. but can it be viewed somehow in that way?
I think this is a super interesting point, and we had like so many experiments and results on this internally. None of this ended up in the paper, just because there was so much other stuff in the paper already. Yeah, so it matters. So as we said, you know, the holdout model can be much less capable than the target model. So it definitely, we have training runs where like the holdout, this model has like 80% accuracy, and this model ends up at 95% accuracy or something like this. So this still works, but yeah, the training curves really end up looking quite different depending on how good this model here is. So there's like funny dynamics. Like if this model is pretty rudimentary, a small model, then that means usually we accelerate training a lot at the beginning when the student model is also weak. But like later on, when the student model becomes stronger, like it doesn't help that much anymore. And when like this, the teacher model is like pretty strong, then actually the training at the start is like pretty slow. It's kind of like the teacher is kind of tells you, oh, look at like these data point next, but the student is like way too dumb to understand these data points at this point in time. And this would better if the teacher gave the students some easier data points. Yeah, and so I think you could do like really interesting things there, where you kind of try to figure out what's like the good like balance there, or where you use like a weak teacher early on and a strong teacher later on, or something like this. Yes, but definitely in the setting, the student can absolutely overcome the teacher here. Yeah.
I see. Thank you so much.
Okay. So here's the algorithm. I think probably has, I think everybody has already kind of inferred this for themselves, but I'm still going to step through it. So we have our data set. First, we go one iteration through the whole data set. And for every point X and Y, we calculate this irreducible loss once at the start of training. Now we start training, and we sample our large batch at each iteration. And then we compute the loss under the current model for each point in the large batch. Now we compute the reducible loss or RHO loss by taking the difference between the loss and the reducible loss for each point. And that is, well, that's our objective. Now we sample the top points based on this objective. So in the paper, we just always use 10%. I think we never really did many experiments with this. We just kind of always use 10%. And we did some experiments, and it doesn't really matter that much. Yeah, so yeah, now, I mean, obviously, it's just sampling the top points is that's only kind of viable under the assumption that that like the scores are independent. So if you assume that, like, you know, sampling 1 point, or like acquiring 1 point would have like little influence on the score of the other point, which actually I think in the online batch selection setting is like fairly valid assumption, because one gradient update on 1 point doesn't change the parameters that much. It's also a very common assumption in active learning, where it's actually less valid, I think. Yeah, and now we have our small batch, and we do a gradient update on the small, well, on the small batch. So yeah, I'm not sure if you explicitly said this, Sören, but so you do forward pass the entire large batch, and then we do the gradient step only on like 10%. So the backward pass only on 10% of this large batch. And so obviously this forward pass needs quite a lot of compute. There are some settings where we're still saving compute overall, because we just need so many fewer gradient steps. That's still overall compute saving. But in some settings, it's actually not compute saving. You have like more compute, but it's still interesting because these forward passes can be parallelized across many machines. And so this enables like a new way of parallelization. that reduces workload time. Yeah, because as Sören said, just making the mini batches larger just doesn't help anymore. Okay, so that's it. And now Sören is going to walk through the results. So I'm going to stop sharing.
Sec. Oh, where is everything? Sorry, just trying to find the right screen. Okay, yes. Can you see this?
Yes.
Okay, wonderful. Okay, so we started by testing our hypothesis that this method will select points that are non-noisy, task relevant, and not redundant, or learnable, worth learning, and not yet learned. We did this on some controlled experiments in CIFAR 10, CIFAR 100, CINIC 10, which is sort of slightly bigger data set, like slightly smaller than ImageNet, all vision data sets. We'll have some MLP results as well later. So starting on the left side, so RHO-LOSS is in blue. Uniform sampling, what you use every day, is in yellow, orange. And then the red and purple ones are baseline methods for selecting points, namely like selecting points with high loss or high gradient norm. And in the left panel, we see we've added some noise. 10% of points are noisy, and indeed the RHO-LOSS selects those points much less often. Whereas we have this failure mode with the prior methods, that they not only fail to deprioritize the noisy points, they actually select them more than even uniform random selection. And this is again because noisy points tend to have high loss. So that's why we'll see later that the existing approaches are going to degrade really badly on data that contains noise, like web scrape data. And then we see the exact same pattern with the less relevant points. RHO-LOSS slightly deprioritizes those, and then loss selection, gradient norm selection in the middle panel. This is massively over-select those points. And then on the right side, we have redundant points. All the RHO-LOSS does well, gradient norm and loss selection. They all successfully remove points that the model already classifies correctly. So that's sort of the easy part. And then now we're getting into this discussion about irreducible loss models. So as Jan said, we made that irreducible loss model trained on a holdout set. We try to make that as cheap as possible by making it small, and also it requires some holdout data, right? Which is also a cost, and we're going to get into that as well. So this is again 3 vision data sets. So first of all, in the top row we have the approach where we actually use a big whole irreducible loss model. So this is kind of expensive, and it's the same size as the target model. And but then in the second row, we've made that irreducible loss model about, I think, about 20 times smaller and 30 times cheaper in terms of flops. So it's a really basic CNN, not a ResNet anymore. And the speed ups we get over uniform selection are about the same. So again, this is speed up in terms of reducing the number of training steps, not compute. So we get speed ups here between, I think, 1.8x and 4x or so on these data sets. And notably, these are quite clean data sets, not super redundant and noisy. So we're going to see even bigger speed ups later. And then in the last row, what we've done is we just did it without a holdout set, because sometimes you have limited data, so you don't want to set away some of that data for your holdout set. And the way we do that is basically we use the training set as the holdout set. So we take the training set, we split it in 2 halves, and we train 2 irreducible loss models, 1 on each half. And then we cross over. So we take the irreducible loss model trained on the first half, and we use it to measure irreducible loss in the second half, and vice versa. So this way we don't need any holdout data, but we have to train 2 irreducible loss models, which is, still in over here, it's still a small fraction of the compute use, because these models are so small.
I wanted to ask the question about, it's a little bit of a lower level question about how you're dealing with the GPU. If you have slides on this, or are going to come to it, or don't want to talk about it, please let me know. But basically, you were saying that you have to do everything in the forward pass in order to get the loss, right, of every point, and then you're selecting 10% and actually doing gradient updates on that. Is that correct?
Mm-hmm.
So that means that, like, if you weren't doing that, if you were somehow magically able to pick the 10% of the batch that you would use, then you could make your batches 10 times larger than they could be, right? And then basically you'd say, like, you're basically getting through the data in an epoch 10 times as fast. But so in practice, then when you sample a big B, right, you actually have to, presumably you can do it in a few different steps, but I would imagine you're either not parallel, or you're limiting your size to what can fit in a big B, and then the little b is underusing the GPU, isn't it?
What we would actually do, so to make sure I understood the question, so we're sampling a big batch, a small batch, and if the big batch, I think you're saying if the big batch fits on the GPU, let's say a single GPU, but then we only train on a small sub batch, then aren't we underutilizing that GPU, right? And the answer is the big batch is going to be split across a bunch of GPUs, so that each of them, let's say we have 10 GPUs, each GPU can only handle like a tenth of the big batch. And so, in the end, we have full utilization of the GPUs, both.
Wait. So you have a batch, and so you've taken those 10 GPUs and you've sent everything through in the forward pass. And before you can do another forward pass, you need to update your parameters, which means you need to do the small b batch through. So then when that small batch is going through on the 1 GPU, the other 9 GPUs are the idle.
Yes. How do we do this again? So you can either, there are different approaches here. You can either just, geez, I guess it's been so long.
If you don't want to talk about it, it's fine.
So I think one thing that is, one easy thing to say here is that, so yeah, all of the big model runs use 1,000 or like 2,000 GPUs, right? And it's not because the companies can't afford more GPUs. Companies would love to spend more GPUs because GPUs are expensive, but I think having your whole engineering team sit around for a month and waiting for the run to finish is also expensive. So one point is, even if you cannot increase utilization, you might still just be like, oh, great, now we have a way to use 5,000 GPUs, which we didn't have before, even if they are not fully utilized. So that's like one very cheap answer. We're like, maybe we don't have to solve it. But I think another thing you can do is like, if you just kind of like use the gradient from from like one step earlier and you do the thing a bit asynchronous, then I think you can shuffle around things that you can get full utilization.
I kind of, so that was, my question was a very detailed way of asking what the more general question is. I think, well, you just showed flops, but previously you were saying you were analyzing in terms of steps. And I guess what I was getting at maybe was like, a step seems to be more like, it's like 9, or it's 10/11ths forward pass and then 1/11th backward pass, right? And so like, it
Yes.
seems like the step size itself, though, I guess, yeah, is that a fair comparison to the like no sampling version where like a step is a step? Here the step is like a mix of this, it's not a full step.
Well, it's only fair under like under the assumption of, well, you have already used so many GPUs that even if I give you additional GPUs, you don't know what to do with them. Under this assumption, it is fair, yes, because you can just parallelize the forward passes and have them on your additional GPUs. And this is the setting that companies are actually in. It's definitely not the setting we are in if you're training on any of the data sets that are in the paper or any of the models that are in the paper. But that is the, yeah, well, that's just that's just what happens if you try to do research in academia, I think. Yeah. Yeah. So maybe another thing is that, yeah, I mean, we have been talking to people from kind of nearly every big language model company, and they're all trying to, well, they're at least asking questions about this. And so presumably they're trying to implement it. Yeah.
Okay.
So I guess, yeah, I'm not, yeah. Yeah, it's really been several months since I last thought about how to like increase the GPU utilization, but I think there are ways, and like one way is to use like asynchronous, to this slightly asynchronous, where you do like where you compute the forward, you compute the losses simultaneously to doing like the update on your previous batch. Yeah, something like that.
You can have,
sorry.
You can have the big batch slide where like you have 9/10 of the thing, and then you're deciding to pick 1/10 of it and use it. And now you have like, you only need like 1 more tenth, and you're just going to use the losses from the previous step or something like that. Seems like you could get it to work that way.
Yeah, then you can basically immediately do like the next backward pass. Because you have, exactly, yeah, while you're doing the first backward pass, right, and you're only using like 1/10 of your GPUs, you're already doing the next forward pass in parallel on the other 90% of GPUs, and then you just always do it like this.
You're just sort of cheating, so to speak, on the forward pass. You're using the last forward pass's results, which eventually can become 10 steps stale for the last little bit before it gets tossed, but those are probably the ones you're not going to pick anyway.
Something like this, yeah. You're using like gradients which are slightly stale, so like 1 step out of sync.
All not the gradients, but the losses are.
Yeah, but then by extension, the gradients will also be stale.
No, because you then train on the small batch using the up-to-date parameters.
Yeah, I think we're all doing something.
Okay.
Oh, that's interesting. I think we never actually did that. I think we always use stale gradients, but this is a good point.
Oh, I don't think so.
Okay, maybe not.
Well, so yes, more empirical results. So this is, we talked about, okay, if things still work, if the irreducible loss model is small, if there's no holdout set, although on one of the data sets it makes a fairly noticeable difference, but I think I forget why that was. But we have more results on this one, and usually works well. And then Jan also made the point that you can reuse the same irreducible loss model to train various target models with across a hyperparameter suite or an architecture search, or maybe you could have the scenario where one you know, one person just trains an irreducible loss model, and then later a bunch of people train on that same data set with different architectures, and they can just all reuse that irreducible loss model across their architectures. Okay, so that part of the course, at least, is pretty manageable. And then let's go into the yeah, how RHO-LOSS actually, how much it speeds things up on various data sets. So here's the vision data sets again, compared to baseline. So RHO-LOSS is the blue curve, and in the top row we just have like the standard versions of those data sets. Each of the other curves is a baseline. On the x-axis we have some accuracy. On the y-axis we have the number of steps required to get to that accuracy. So it's lower is better. So it's kind of flipped for well, I won't get into it, but it's sort of the flipped version of a normal training course that you see. And yeah, it's consistently training faster than the other selection methods, uniform selection and various baselines. And then in the bottom row, we've added noise to sort of simulate the noise you'd have in web scrape data, for example. And you see that the speed up you get goes up the more noisy the data is. Whereas because these baselines like loss selection select all the noisy points, they sort of degrade and can no longer compete with uniform selection, even because they're selecting all noisy points. This same sort of pattern is observed on we don't have many NLP datasets, but we've done COLA here and SST2, which are part of the GLUE benchmark. And we've highlighted apparently the 10x speed up on COLA over uniform selection. So again, RHO-LOSS is the blue curve here. This is for fine-tuning BERT, or was it Roberta? And then where RHO-LOSS shines the most is on relatively big web scrape data. So this is a vision data set, clothing 1M, about the same size as ImageNet, but it's web scrape, which means it's quite noisy. And this is where we get that 18x speed up. And in the graph here, you see uniform is on the bottom, the orange one, RHO-LOSS is blue. And we want to see how robust this is across architecture. So each of these thin little lines is one architecture, like ResNet, MobileNet, DenseNet, Inception, and GoogleNet. And here, because the data set is quite big, we can just take a holdout set, 10% of the data, and that's actually more than enough to train a pretty good holdout irreducible loss model. And overall on this data set, we also have some savings in terms of compute, in terms of flops, rather than just training steps. Okay, that's already time to conclude. So yes, I think we can actually prioritize questions over going through this again. There's some interesting follow-up work from people at Mila who applied RHO-LOSS to reinforcement learning as a drop-in replacement for prioritized experience replay, and works really well, but probably less interesting to the NLP crowd. So yeah, thank you. And any further questions, let us know.
We will now open the floor for questions. Who has a question?
Sehr interessanter Vortrag, Dankeschön. I've got a question. So you very cleverly use your techniques to classify training examples into the easy, the worthy, and the unworthy, and then focus on the worthy. With your approach, could you also identify misfits that might be mislabeled, ambiguous, and weird? So this might be used to improve data sets or even validate your progress by showing that you're able to identify these misfits that are unworthy.
Yes, this has already been done in prior work, but one method of doing just finding mislabeled points is to train a model on a holdout set and then evaluate its loss on your main data set that you want to filter down, and yeah, points with really high irreducible loss tend to be mislabeled pretty often.
Wait, so can you do that then right at the beginning and then not have to bother even encountering them anymore?
You can do it at the beginning. There would be like a core set selection method where you just do it sort of offline. This would be like offline. We do online batch selection. This would be offline selection. This has, so one reason it doesn't work so well, like we've also done this as a baseline. Actually, I don't, yeah, it's one of these lines and it's not one of the better ones. Well, this doesn't remove redundant points, right? It doesn't help you skip the points that the model has already learned. It only skips the points that are like really noisy or less relevant.
No, I don't mean to only do that. I mean, you just start off by removing the noisy ones and then continue on with the rows.
That's interesting.
And I wonder if you're if you assume your data just has redundant or unlearned or whatever regular elements in it. I don't know if that leads to any further assumptions you could make. But even without that, if you just had smaller data, then you essentially remove the need to do the forward pass on that data. Right?
Yeah, I would have to think through like how promising this looks in detail.
I mean, one thing to add is, of course, that, I mean, the setting for which this RHO-LOSS method is like most promising is like the setting where you have like tons and tons and tons of data. And then as of now, at least, companies anyway only train a single epoch, or quite often only train a single epoch. So yeah. There's no difference between doing it ahead of training or doing it online. You'd still do it only once for every point. I think if you want to reduce noisy points ahead of training, this is probably one of the best methods. But not we haven't tested this. It's not necessarily the best. There's this metadata archaeology paper from like a month ago from David Kruger's lab in Cambridge, where they look on the time. They look they look at the time series of the loss over training, and then they show basically, oh yeah, mislabeled points have like characteristic trace basically that might be even have even better sensitivity and specificity for detecting mislabeled points, because it's really designed for this purpose. But yeah, you can definitely, yes, combining this with like some offline methods could be a good idea. Yeah, they don't give you any of the online benefits of, you know, dynamically selecting those points that like your model has not yet learned or something like this. But they could do something like filtering out the noisy points. Yeah, could work.
Do you have any experiments that you've done with language modeling and specific insights related to that you could share? I know one of your co-authors is a CEO at Cohere, so I'm pretty sure it is of interest to be able to filter out noisy language, text data to train a better language model. So
yeah, I've done like a little research on this. With BERT models. I haven't tried it too much because I wanted to shift my research more into the safety and alignment direction, because I just kind of thought there's like so much to do there, and it seems really important. But from the little that I've tried, yeah, I didn't get like massive results. I think the best I ever got with BERT was like a 2 or 3x speed up. So it was nowhere near as good as like our 20x speedups that we got on with the vision datasets.
This is for masked language modeling, by the way.
Yes, yes, I
so
only tried
pre-training
masked
phase.
language modeling. So what I tried everything kind of like no, I didn't try everything. I tried like kind of sequence selection. I tried like, mask selection, kind of like masking those tokens with kind of the highest RHO loss basically. And then different ways of like randomly selecting those masks and so on. So yeah, I mean, all I can say is I never got it to work very well, but maybe I would have gotten it to work well had I worked more on it. Yeah, I just wanted to do other things. But yeah, I mean, I think probably somebody's working on it right now.
And with Cohere, the intern who was supervised by Aiden stopped internship at some point. So the work just couldn't continue. So we didn't get very far.
Yeah, Cohere hasn't done it as far as we know. Yeah.
Okay, cool. Thank you.
Since we are a bit over time, if you have any more questions, please feel free to reach out to Sören and Jan offline. I would like to thank you for joining us today, and I would like to thank Sören and Jan for the really great talk, and see you next time.
Thanks so much.
So much.
It was a pleasure. Have a great day.
Great questions as well.
Yes.
Thank you so much.
Bye-bye.
Cheers.
Peter, can you
Cheers.
please stop the recording?